thanks everybody for having me, and thank you Regression and Jamie for organizing this speaker session. Yeah, so I'm here today to talk about automated regression methods for Turbine-Penstock modeling and simulation. It's a bit of a big name, but really what we're getting at here is a methodology that American governors utilized to essentially take a theoretical model of a power plant and fit it perfectly to the actual power plant, any particular, real power plant out there in the world. Essentially, the challenge here is that with pump storage facilities, oftentimes there's incorporation of certain hydrodynamic components which make the system, model essentially nonlinear. When you run into these nonlinear considerations, the modeling aspects become much more challenging, and the methodology for solving that and fitting it to a plant becomes more challenging. The inspiration for this particular case study was derived from Castaic pump storage power plant. American government has the contract to upgrade all of the 6 main reversible pump units, as well as a new contract for the 55 megawatt impulse unit. Some basic facts about Castaic: it's located just north of Los Angeles and supplies a lot of base load and peak power demand to the city. As we said, there's 6 reversible main units. They're rated at around 270 megawatts, depending on if they have gone through mechanical upgrades. And as we said, there's also an additional impulse unit, which was originally designed with the intent not only to provide generation capabilities, but also serve as the pump starter for the entire plant. We see here it's got about 1,000 feet of head, and it's coming in an installed capacity of around 1.5 gigawatts. Here's a basic elevation view of the plant. We can see, on the far left, essentially, we're illustrating a surge tank, and from there we go downstream to the power plant. There's 6 separate penstocks, each one feeding a main unit coming out of a common header. But in this case, our main focus here is that we have a surge tank as well as these independent penstocks. So the methodology American governor came up with in order to accomplish the task of taking this virtual model and fitting it to a power plant is listed here. It's a series of steps that we followed in order to make that possible. Step 1 being we have to select the model. Oftentimes, if you consult academia, if you consult the literature, you can check out IEEE working groups. There's a lot of literature out there. There's a lot of different models out there that can, in their own ways and in their own regimes, do a good job representing any given power plant. But doing a great job or handling something with more hydrological complexity becomes the challenge. So in selecting the model, American governor went through a series of research papers and was able to uncover a fairly effective model by Oscar Daniel Quiroga, who is a doctoral candidate. He developed this model to account for, as we say, a surge tank and some of the other hydrological effects. Mainly, the consideration is that upstream of the surge tank, we can consider a water column flowing through that main feeder tunnel to be an inelastic water column, meaning that pressure fluctuations really aren't affecting the flow or the level of that water because we're sort of buffering those through a surge tank. Of course, then, we see in the middle section of this math model, we have dynamics accounting for the surge tank itself and how that affects water flow through the unit and how that affects, in turn, the speed of the unit. Basically, if we take that math model and resolve it into equations, we see we have a series of 6 equations. I don't even really need to get into the particulars of any of these equations. It's illustrated here just to show it's kind of complex. But even with these 6 equations, this isn't able to fully define something like a real system at Castaic. So what we needed to do at American Governor is essentially come up with a series of equations which would link this theoretical model to the power plant itself. So we have another series of equations, all of which are a little daunting just to consider. I haven't listed out all of the coefficients and variable names here, because it's really just to illustrate the point that these systems become notably complex, and an exact numerical solution, or should I say an exact symbolic solution, something you could actually write down on a piece of paper and get an answer, is essentially infeasible in this circumstance. So what we do with these equations, we were able to link everything together, link Quiroga's model with some of our heuristic-based equations to come up with a state space model, which is really the most useful and capable tool for doing numerical analysis. So with this numerical formulation, we essentially, it's hard to tell here, but this is actually a power plant. This is a Turbine-Penstock system. except it's written mainly in a form that the computer would be really happy with. So we take this system and we model it in a numerical computation program, not unlike MATLAB. In our case, we used a different solution, but MATLAB would be able to do the exact same sort of work. We take this model and plug it into the computer. And now essentially we have this model, but it's just a theoretical model. All of the coefficients and all of the things which would define it and make it represent Castaic power plant or any given pump storage facility, for that matter, have yet to be defined. So in our case, we then proceed into validating this and turning this into a model which would fully represent Castaic. In order to do that, we have to go through and actually collect performance test data. We went through Castaic. This was long before we upgraded any of the digital control systems. And we basically had the operations team run through a series of step tests and load rejections and things of that nature. And the whole time we're acquiring this with a data acquisition box. So we could then take that data and put that in the computer as well. So we have our skeleton of a model, essentially, with all of this plant data. And what we then had to do was run a regression technique in order to take that data and sort of mold and shape the theoretical model and turn it into the Castaic power plant. And we see after we've done that, we ran through a cost, essentially a cost minimization function. This is an optimization routine we ran in that numerical tool. Essentially, it's a 13-dimensional optimization problem because it's accounting for all of those coefficients and all those things which have yet to be defined. But we can see what we get after we run through this numerical routine. It took about, I want to say, probably 50 hours of number crunching on a standard personal computer. But that's not me plugging away at numbers. That's an automated technique. So we're able to just kind of set up a computer, let it run, and do its thing. And after 50 hours, we come back and we have all of the information we needed to define Castaic. So we can see here, we have a breakaway routine, we have a load rejection routine, and we can see that our speed, it's almost hard to see in certain sections, but we have a measured and modeled speed, and we can see that they're in good agreement for most parts. When we get down near the lower end, we have some issues with the way that they ran their high pressure lift pumps and how that affected our model as compared to reality. But for dynamic, online testing, anything where you'd be up to standard speed, we can see very good conformance with the real plant data. So what's pretty cool is after we have this model and what the real application of all of this can be, is that we now have something that we can test on. We can take this model and put it through the ringer. We can give it step changes. As the governor guys, we're concerned in speed stability. We're concerned in how you can load the units. And in this case, we can sit in our office essentially long before commissioning, long before we have to schedule major outages or deal with any of those considerations, and play around with the system and tune those PID parameters and our underlying control parameters ahead of time. And additionally, when we're online, we have some methods of primary power control, which we also could tune in and see how it conforms. And here we're just showing the regulation equations that we use. And in order to get there into the system and start messing with things, we can see if we're talking about regulating speed, we have a speed reference that we can adjust virtually and see how the system responds. And in power control mode, there's an inherent megawatt set point which we can adjust and play around with. So really, once we were able to develop that model, we could go in there, play around with the gains, with the settings, and tune our system, tune our virtual power plant before we got to site. The next step, which was really kind of the rewarding part of the whole process, was being able to go back to that facility, and on that first commissioning of the new digital control systems we were putting in place, we were able to take a look at how our theoretical values, how our experimental values in the virtual world compared to that of the real world. And we can see here we have a few graphs just showing, this is on the unit itself with the gains as established through simulation. So we can see that we have, essentially in the blue line below, we have the speed, or the gates being depressed. The wicket gates are being artificially restrained by the gate limit. And we see that the speed up in black starts to drop down. And once we see it start to stabilize at a lower level, one of our normal commissioning practices is to get that out of the way and see how the speed responds. See if the governor is doing its job, if it's holding speed correctly. And we can see through simulation, we have a little bit of under-damped conditions here. So we have speeds ringing out a little bit over time. The gates are a little aggressive, and the speed is, as a result, a little bit oscillatory. But all in all, we have a stable system through our virtual tuning method. We can see that after commissioning, we were able to fine-tune things and develop a little bit more stability. But we're not too far off from the response we were looking for initially. And in the same way, we have a megawatt response from simulation. Again, we're a little underdamped. Some of our underlying tuning parameters, we're not exact due to time and cost considerations as well. We were able to develop something that was controlling power. We were able to regulate to a certain degree of effectiveness. But of course, and albeit this is on a different time scale, but we can see that after the commissioning, we had made a few fine tweaks and were able to develop a system that was controlling power most effectively. So really, the cool thing about this whole process, and it's something that's repeatable, it's something that can be really tailored to any particular power plant, especially when you consider these pump storage facilities or other standard generated facilities that would incorporate some interesting hydrological components. We can take this sort of methodology and apply it to any given number of plants and provide any end user essentially the virtual version of their plant. This can be utilized for, as we've done in this case, hydrodynamic response planning. We can see what we need to do as far as PID gains, as far as our megawatt feed forward parameters, as we've said. But what's also interesting is if anyone here is involved in a pump storage facility, especially some of the larger ones like Castaic, it's very crucial to not only grid stability, but just overall grid maintenance. We need that system online in order to provide enough power to Los Angeles. Part of that, as far as considering new ideas, we have been in conversations with WEC, WECC in this case, not the world version. But in that sense, WEC has had discussions over, should we change the way that we set these governors up? So the actual concerns over grid stability can go beyond the unit view itself. And if you're starting to consider how those would affect different plants, or how that would affect the grid as a whole, you can actually virtually try to come up with a new scheme. At Grand Coulee, for instance, we use a lead-lag controller, not a PID. There's other methods of control algorithms that could be tested in any given scenario, so it gives you some advanced planning capabilities. And additionally, as far as applications, we also have a great opportunity for training. If you have any virtual simulator, you can essentially, have a great model of the plant. So operations people, anybody that's testing or learning how the system works, they have something that really does emulate the system. It's not, just sort of a fuzzy representation. It's a true to form representation of the system. And just finally, also, anybody who's involved in troubleshooting would know that it might often be nice to be able to test something without having to spin the unit up or schedule an outage or handle, that situation on the real equipment. So it's another mechanism there to have this virtual means to go about it. So yeah, just in closing, I'd like to give special thanks to the people listed here for helping on this development effort. Thank you.
We have time for one question. Yes, please.
Since you have such a good model of your system available, can you consider using a more sophisticated control scheme than a PID controller?
Well, in our case with Castaic pump storage, well, we've found that we generally have the conformance we're looking for, and in that case, we haven't moved to any more advanced control apparatuses. Obviously, they're out there, and they all have sort of pros and cons. So in our case, we thought it made sense to stick with a PID, although it would be noted that in that particular situation, those standard sorts of gains did need to be tweaked quite a bit in order to provide a stable system.
One more question? If not,